So I welcome you once again to Winkell's class, and today's content is about Aldol reactions, as you can see on the board. Before we continue, or before we even dive more into today's content, I would like to remind you that I have a video on carbanions, what they are, and explaining the actual contents of carbanions, like how they are formed, how they can be stabilized, and then the things that they are made up of. Okay, and I'm going to put the link to that video in the description section so that if you need any recap or you'd have to go and watch that video before coming right to the reactions, that would be very helpful, and then it will also help you to keep yourself updated as we go through this particular lesson. Okay, now I would also like to inform you that with this is just the beginning. Okay, and then we are going to be having series of videos pertaining to the different reactions that carbanions undergo when we come to chemistry, all right, organic chemistry for that matter. Yeah, so let's look at what we have today. Specifically, we are just directly talking about carbanions, okay? And we said that from the previous video, we made mention of the fact that carbanions are organic species, okay, that are usually having a negatively charged carbon atoms, okay? And then those carbon atoms are usually having sp3 hybridization. So what we are trying to say is that when you want to describe what a carbanion is, you want to see this particular feature in the molecule that you are using. Okay, whatever molecule that you are being given, you want to see this particular negatively charged carbon atom in the species. Okay, right? But then when you come to our world, okay, for the purpose of this video and then the the target of this particular course, all right, we are going to be dealing with carbanions that are involved in carbonyl compounds. Okay, and when we say carbonyl compounds, we are looking at organic compounds that has this particular functionality, carbon double bond functionality. Uh-huh. And we know that there are several kinds of carbonyl compounds. We have the aldehydes, we have the ketones, we have the esters, and so on. But we are going to be looking at them individually, and then we'll see how they all fit into this particular course. All right, good. So now that we have recapped a bit on what carbanions are, we'll look at the main content for today. Okay, but before we do that, please don't forget to subscribe to the channel if you are new, and also don't forget to like the video, share it with your friends for them to also benefit from what you are watching right now. And also don't forget to turn on the notification bell so that anytime I release a video, you'll be the first person to have access to it. Okay, good. So we looked at carbanions and then we know what they are about. Now we want to see the kind of reactions that they undergo. Okay, when you come to organic chemistry, when you are dealing with a particular group of molecules, all right, we look at the specific reactions that those molecules undergo so that we can apply them in producing products that can be consumable, products that can be used in other aspects of our lives. Okay, so the most important aspect of this course or this series of videos that I'm going to be doing has to do with the reactions that we are going to go through. So please pay much attention and make sure you grab the concept from here. If I say something that you didn't hear well, or you felt like maybe I spoke very quickly, you can pause the video and then look at it very well and then play it again. Okay, it's helpful when you pause the video, try to analyze what I said, and then you continue playing. All right, now Aldol reactions is one type of reaction that carbanions undergo, okay, and then it is under a particular group of reaction that we call carbonyl condensation reaction. Okay, we call carbonyl condensation reaction, right? So carbanions usually undergo series of reactions, and then a general name given to those reactions what we call carbonyl condensation reactions. All right, those reactions involve the use of two partners. All right. If I say two partners, it means that for you to be able to undergo a carbonyl condensation reaction, all right, we need two molecules. All right, it could be the same molecule, it could be two different molecules having the same or similar properties. Okay, so you could have a carbonyl condensation reaction occurring between a ketone and another ketone, or an aldehyde and another aldehyde, an ester and another ester, or a ketone and an aldehyde. Do you get it? Yes. So we need two partners for such a reaction to occur. And also, as the name implies, a condensation reaction, which means that there's going to be what? Expulsion of water, right? We are going to be removing water out of the system. That is how come the name condensation. So keep it in mind that because we are dealing with carbonyl condensation reaction, the reaction is going to involve what? Carbonyl groups, which are esters, ketones, aldehydes, and so on. And then because it involves condensation, we are going to be dealing with the removal of water from the system. Okay, so that is the general idea behind the whole reaction. All right. Now, we are looking specifically at one of those carbonyl condensation reactions. With regard to the condensation reactions, there are several of them. We have the Aldol reaction there, we have the Claisen reaction, we have Dickman reaction, we have the Robinson annulation. There are several of those reactions, and we are going to be tackling each and every one of these reactions in a subsequent video that I'm going to do. All right, but today we are focusing on the first of those reactions, which is the Aldol reaction. All right, in the Aldol reactions, there are some specific things that we need to keep in mind. Okay, the first thing that you need to know is that it involves only aldehydes and ketones, no esters. Okay, so with the Aldol reactions, it includes aldehydes. Let me put it this way, and then it includes ketones. Okay, this is a ketone, this is an aldehyde. You know, aldehydes, they are also carbonyl compounds, and then what differentiates them is that the carbon bearing the oxygen, which we call the carbonyl carbon, usually has one hydrogen attached to it, at least one hydrogen atom attached to it. All right, that is what makes it an aldehyde. But when we talk about ketones, there is no hydrogen atom attached to the carbonyl carbon. All right, so this is a ketone, and then this is an aldehyde. And we are saying that for Aldol reactions, it occurs among what? Aldehydes and ketones. So you could have two ketones reacting, two aldehydes reacting, or a ketone and an aldehyde reacting. All right. When it comes to this reaction, okay, the Aldol reaction or the carbonyl condensation reaction for that matter, the catalyst that we use here is a base. All right. We usually use a base as the catalyst. And what does the base do? You know, bases are known of their property of what taking protons from a system, right? They abstract protons from a system. Good. That is the main purpose or the main reason why we are going to be using a base in our reaction. We need the base so that we can easily form the carbanion. If you have watched my previous video, you would know how carbanions are formed. And once I mentioned that we are going to be using a base in this kind of reaction, then you know the purpose or the reason why we are bringing in a base. Okay, the base is just coming to help us what abstract the proton from the alpha carbon so that we can form a carbanion. All right, don't get confused at all. If you haven't watched the video, you can go back and watch it, and then you come back to this content. It will help you understand it more clearly and then more simply. All right. Now we know the condition, which is we have to use a base as the catalyst. We know the reactants, which are either a ketone or aldehyde. But then don't forget, because it's a carbonyl condensation reaction, we need two partners. So it could be aldehyde of the same kind, ketone of the same kind, or a different aldehyde and a ketone. All of them combining together. All right. Good. Now let's look at a practical example. Let's see how this reaction occurs. We want to look at the mechanism that is involved in this kind of Aldol reactions. All right. So if I use this basic ketone, for example, all right, this is the basic ketone that we can use, and because we are dealing with an Aldol reaction, you know what to do already. We need a base. All right, we need a base. This is our base. Okay, good. And what is the work of the base? The base is to help us what? Form a carbanion. All right, the base is here to help us form a carbanion. And from the video that I made regarding how carbanions are formed, what do? We know that carbanions are formed when the alpha hydrogen attached to an alpha carbon is what? Abstracted. Okay. When you take a carbonyl system like this, the carbon bearing the oxygen is what we call the carbonyl carbon, right? And then the carbons that are directly attached to the carbonyl carbon is what we refer to as what? The alpha carbon. Okay. Now, you see that these alpha carbons, they have hydrogens attached to them. Okay. This has 1, 2, 3. The same way this one also has three hydrogens attached to them. Right. Good. Now we want to quickly form our carbanion. All right, we have started the reaction process already. Okay, so now keep it in mind for this Aldol reaction, the first thing that you need to do, or the first part of the mechanism, has to do with the formation of what? A carbanion. That is the first thing, and that is what we are doing here. Okay, now we have our base, we have our carbonyl system. Okay, let me clean this part of it so that it will look more clearer. Yes, now we have our base. If I have my base here, why is the hydroxyl group having a negative charge on it? It means that the hydroxyl group has what? Excess electron in the system already. So it doesn't need electrons. Is that not it? So it's going to act as what? The nucleophilic donor. Do you get it? Now, when you come to our alpha carbon, we are using this alpha carbon for the demonstration. Okay, I could have used this. You can also use this because they are all directly attached to the carbon. They are all alpha carbons and it is symmetrical, so you can use any of them. All right, but for the purpose of this presentation, I'm going to be using this one. Okay, and as I said, this carbon has 3 hydrogens attached to them, and all of these hydrogens are the same because they have what? The same chemical environment. So you can abstract or work with any of them. Okay, good. Now this is our base, which is rich in electrons, and then it needs to be able to what? Donate this electron or share the electron with a particular species. All right, and that species in our case here is what? A hydrogen atom. Okay, now hydrogen exists like this as an atom, but then when it exists like this, it is called a proton, right? It is called a proton because there is no electron in its on its shell, right? There is no electron there, so it becomes what? The whole system becomes full of protons. There are no electrons in there. That is why we refer to this H plus as what? A proton. Good. Now the base does not come to abstract this hydrogen atom. Rather, it abstracts a proton. Okay, it abstracts a proton because the base, which is this hydroxyl group, it is already having an excess electron that it is willing to share with whatever species that will be coming close to it. Okay, so it is not interested in the electron that the hydrogen possesses, but rather it is interested in what? A species that doesn't have an electron, or a species that is in need of electron. And with that, a proton is a perfect species that can do that. Okay, so instead of us abstracting just the hydrogen atom, it doesn't happen that way. Rather, the hydrogen atom donates its electron, the electron that this hydrogen is having, it places it on the carbon here so that it can become what? A proton. Okay, and once it becomes a proton, it gets easily abstracted by our base. Please, are we following? Right. If you have not followed up to this point, you can pause or replay the video, go back and then follow it carefully. You will get it. It's very simple. All right. So just remember, the first thing we are doing here is we are trying to form a carbanion. All right. And how do we form the carbanion? That is what I'm explaining here. Good. Now we have our base ready to abstract our proton. And as I said, this is a hydrogen atom bonded to a carbon. And anytime you find a dash, this dash a dash like this connecting two elements or two atoms in organic chemistry, we refer to this as well a covalent bond, right? And then a covalent bond requires that the two atoms involved in the bonding share electrons with each other, right? So every dash that you see represents what? Two electrons, right? Every dash represents two electrons. Is that not it? Good. Now, because our hydrogen here, we need it in the form of a proton. What happens? Don't forget, one of these electrons was donated by the hydrogen and the other was donated by what? The carbon. That is how come the formation of this covalent bond, right? Now, for this hydrogen to become a proton, what happens? The electron that the hydrogen possessed, it will be transferred onto this carbon. Okay. When that happens, this carbon ends up having this. It ends up having the two electrons attached to itself, whilst the hydrogen has none of the electrons. And when that happens, the bond breaks. Okay. So it's like the two electrons in the bond, all of them gets transferred onto the carbon, making this carbon negatively charged and making our hydrogen positively charged because the hydrogen also doesn't have any electron anymore. Do you get it? So this same idea or this same scenario comes to our main work or our main project. All right. Now, what do we do? As I said, there is a covalent bond between the carbon and the hydrogen. And because we want to make this hydrogen positively charged, what do? We transfer the electrons within the bond onto the carbon. Okay. Let me use a different color so that you appreciate the movement very well. So yes, the bond in between the carbon and the hydrogen gets broken onto the carbon. Is that not it? Right? Now our carbon becomes negatively charged, right? Because it is having excess electron that is coming from the hydrogen. Okay, and then the hydrogen becomes positively charged. Why? Because the electrons that it had first, or the electron that it was sharing with the carbon, all of them were transferred away from it, so it becomes positively charged. And when that happens, it is now convenient for our base, which is highly negative, to come and pick the hydrogen in terms of what? A proton. Please, are we following? Good. Now that we have been able to successfully abstract the proton with the help of our base, which is the catalyst here, now we'll proceed with the second step. Okay. In the Aldol reaction, as I said, after you have formed your carbanion, don't forget we need to stabilize the carbonyl system. Okay. Now the carbanion that we have formed, we need to stabilize it through the process of what? Resonance. All right. Now, see, I've forgotten to write the carbanions. Yes. So to just simplify what we have gotten, okay. This is what we use the simplest ketone, which is this. Is that not it? Now we have one carbon atom here. It is there, which is this one. And then this carbon atoms now becomes negatively charged. So it becomes like this, negatively charged. Is that not it? This is what we call our carbanion. Okay. This is our carbanion. And as I said, we need to be able to stabilize this carbonyl system. Okay, we need to be able to stabilize it through resonance. Let's delocalize the charge throughout the system so that it doesn't get concentrated at one part of the molecule. All right, and to do this, we use what? Resonance. Resonance is represented with this two-headed arrow. All right, double-headed arrow. Once you see this, it represents what? Resonance. Okay, and I'm going to put this in a square bracket. All right. Now, how do we resonate or how do we delocalize this electron throughout the system? Don't forget the negative charge here. Okay, the negative charge here only shows that this carbon has what? Excess electrons on it. Is that not it? Right. So for us to be able to delocalize this electron throughout the system, what do? We move the electron, instead of the electron being on the carbon only, we now bring it into the system. So now the electron here is going to be shared by what? The carbonyl carbon, which is this carbon, and then this alpha carbon. Okay, so the electron now is being placed in between these two systems. All right, good. Now we know that in chemistry, carbon can only have a maximum of 4 bonds. All right. Once the bonds are more than 4, it's a haram. Okay. Yes, it's a haram. It is not done in chemistry. It's not possible. All right. So, in order to maintain that principle or that fact that carbon needs to have 4 bonds maximum, what do we have to do? Once we have broken this, or we have placed this electron in between these two carbon atoms, okay, making them have excess electrons around them, we need to be able to break one of these bonds. For that matter, we are going to be breaking the pi bond in between the oxygen and the carbon. This oxygen and the carbon, we need to break the pi bond between them so that the carbon can easily form its 4 bond without breaking that principle. Please, are you following? So for you to be able to show me what is happening, you need to tell me or show the arrow that one of these bonds is also breaking. Okay. So as you have delocalized this electron into the system, okay, being shared between this carbon and this carbon, what happens? The bond in between the carbon and the oxygen here, one of them, or the pi bond, gets broken onto the oxygen, making this oxygen highly negatively charged as well. All right. So what do we get when we do that? This is what we get. We end up having this negative charge here, and then we end up having a double bond here. Don't forget. Yeah, don't mind my lines. Yeah. So we end up having a double bond here. Yeah, because you could see that this carbon is this carbon, right? The negative charge on it is no more there. Why? Because the electrons here is now being shared between these two carbons. So now it has formed what? A double bond in here. And to prevent this carbon from having 5 bonds, we broke one of the pi bond attached to the oxygen to have what? To make it what? Negatively charged. All right. Now I'll put this in a square bracket. And this species is what we call the enolate ion. Okay. This species is what we refer to as the enolate ion. Whilst this one is what we call the carbanion. Okay. So now don't forget, with what I just did, every carbonyl condensation reaction that you are going to undergo or you are going to write the mechanism for, do not forget to balance or stabilize your carbanion through resonance. After you have formed your carbanion by the abstraction of a base, don't forget to stabilize the carbanion to get an enolate ion. Okay, once you have done this, it means that now your carbanion or your carbonyl system is ready for the next step of the reaction. All right, so now this is our resonance system. Okay, we have gotten our carbanion and we've got our enolate ion. Okay, now we want to proceed. The second step of the reaction has to do with what? The reaction of the carbanion that you have formed, okay, with the second partner of the system. As I said, the carbonyl condensation reactions occurs within what? Two partners. And the first one was what we used to form the carbanion. Right? Now, what is the second one? If you remember, when I started the reaction process, I used this ketone throughout the system, right? And then I also made mention of the fact that the base that we use should be a weak base. Okay, good. Now we are using a weak base because when the deprotonation process is occurring, okay, when the formation of carbanion is occurring, we want to use a weak base so that the base does not end up deprotonating all the reactants or the ketones present in the system. Okay, we don't want all the ketones present in the system to get deprotonated. So because of that, we use a base that will not have the ability to deprotonate all of them. It will only deal with a few of the starting materials so that we can have some of them remaining in the system unreacted or untouched. Please, do you get it? Let me represent this with a specific example. Let's say, for example, we have 3 moles of this particular molecule in a solution. Okay. Now we want a reaction that will occur, okay, that involves part of this being reactive and part of this being unreactive. Okay, now what do? We need to set a condition that will make this possible. All right, now that is what I'm saying, that the condition that you need to set in order to make this possible is the use of what? The weak base. All right, so you use a base that can only convert one or two of this into a carbanion. So let's say the base has the ability to convert just two of this into a carbanion. Then it means that we still have one of this remaining untouched or unreactive, right? So far as our base cannot convert all these three into a carbanion at that same time, the condition is suitable for us to be able to what? Convert or produce a carbanion and still have our normal ketone remaining in the system. Okay, that is what I was trying to explain. So the basic idea here is that we use a weak base, okay, so that the base does not end up deprotonating all the reactants or the ketones that you are dealing with in the system, so that some of them will be remaining in the system untouched. Do you get it? Good. Once you've gotten that, let's proceed. So you bear with me per the explanation I just gave, that because I used the weak base from the beginning, okay, it wasn't all the initial reactants that were converted to what? A carbanion, and for that matter, an enolate ion, right? It means that some of the ketones were still remaining in the system, okay? And then the one that untouched or that unreacted ketone that is still remaining in the system is what we refer to as our second partner. That is the second partner of the reaction that is going to add up or react with our carbanion or our enolate ion in order to form our Aldol product. Please, are you following? Good. If you are confused, don't forget you can pause the video, replay, and then get the understanding before you continue. All right. Good. Now, what do we have here? As I said, we have our ketone in the system, part of it unreacted because the base that we used was what? A weak base, right? So this is it in here. Now we have also converted some of them into what? Carbanions, right? And they are already in the system. So it's like a mixture of carbanions and then what? Normal unreacted ketones, right? So now this is, let's say, this is the ketone that was not reacted with any base, or the ketone that remained untouched in the system, right? Now, because we have successfully converted some of this into carbanions or enolate ions, this will now either the enolate ion or the carbanion will now come back to react with our unreacted ketone. Okay, you could see that now they are of two different species. This one has no charge on it, but this, either the carbanion or the enolate ion, has a charge. So now once you bring them together, they will end up reacting with each other. All right, good. Now it is your choice as to whether you use the carbanion for the reaction or you use the enolate ion for your reaction. It is your choice. But then, for the purpose of clarity here, I will use the carbanion for the presentation. Okay. So now I'm going to use the carbanion aspect of it. Sorry, my marker. So I'm going to use the carbanion aspect of it. Okay. So yes. Now this is my carbanion reacting with what? The remaining ketone in the system. Okay. Now we have a carbanion and then what's a neutral ketone in the system. Both of them reacted. Is that not it? Yeah. This is the continuation. Okay. This is just a continuation of what we have. So after you have formed your carbanion, you have stabilized it with resonance, then you proceed with this part of the reaction. Okay. Good. Now, what do we have here? There is a negative charge here. But how is it possible for this negative charge to react with this neutral system? Okay. Now, the same procedure through the process of polarization. When we talk about polarization, it's like an equal sharing of electrons within a system. All right. Let's say, for example, if I have, let's say, chlorine here, and then I have hydrogen here. Okay, when we talk about polarization, under normal circumstance, the two electrons are supposed to be in the middle so that they can equally be shared by the two species, the chlorine and then the hydrogen, right? But then, for the purpose of polarization, okay, what happens is that because chlorine is more electronegative than hydrogen, it pulls the electrons more closer to itself than the hydrogen. So instead of the electrons being in the middle, the electrons shift closer to the chlorine as compared to the hydrogen. And when that happens, we end up creating partial charges on these two species, right? We create a partial positive charge here and we create a partial negative charge here. Why? Because the electrons which are negatively charged are more closer to the chlorine. That is what we call polarization. All right. That same idea is what we are going to use over here. When you take this carbonyl system, this is a carbon and this is what? Oxygen. And between carbon and oxygen becomes more electronegative, right? And because oxygen is more electronegative, what do you think? The electrons within the bond will pull more close to oxygen as compared to carbon, right? So you end up creating partial charges within the system. And what are these partial charges? You have a partial negative charge on the oxygen and partial positive charge on this carbonyl carbon. Okay. But then it's not really necessary for you to write it, but for the purpose of your understanding, that is why I'm explaining it this way. Okay. So now that we have this charge in the system, you know, they said that the rules or the law of magnetism, like poles repel and then unlike poles attract, right? Yes. So this is a negatively charged species. This is a positively charged species, and then they can easily attract, right? If you are using the law of magnetism. Good. So our negatively charged carbon here attacks the positively charged carbon in the ketone. Okay, and as I said, to prevent this carbon from having four bonds, what happens? One of these bonds has to break onto the oxygen so that we can establish that stable system. All right. And once you do that, what do you get? Now, this is where most of us get confused. So take your time and look at what I'm going to do over here. All right. We have our carbanion reacting with our normal ketone. The carbanion is negatively charged, and because of polarization, this carbonyl carbon is what positively charged partially. So there was a reaction, and to prevent carbon from having four bonds, what happened? The bond got broken onto the oxygen, right? Good. Now, what do we have? For us not to get confused, okay, what you have to do is, don't forget now you are combining two systems, so you expect your molecule to become more bulkier, right? It becomes more longer and bigger as compared to the initial ones, right? Yes. So when you get to this stage, okay, pay attention very carefully, okay, because this is the part that most of us get confused at. All right, so be very careful with this. When you get to this part, I'm going to take my time to explain this part, okay. When you get to this part of the mechanism, all right, what you have to do is that check where the connection is happening, okay. You realize that it is this carbon, all right. Let me just do an asterisk against it. This carbon that is what's attacking this carbon. Another asterisk here. This carbon that is attacking this carbon, right? So if I want to draw a connection between them, you realize that it is just following the arrow is going to be like this. Is that not it? Good. What you have to do is just count the total number of carbons within the connection. The total number of carbon within the connection. I mean, the two species combined together, the total number of carbons in them. You count it. So watch me count. How do I count? You can start from any direction, okay? I would love to start from here. You take, I'm going to count 1, 2, 3, 4, and 5. You realize that I didn't count this particular carbon or this particular bond to it. Why? Because this bond was not connected to this system. Okay, so it's like as a connection. You have a connection, there is a break. Another connection, there is a break. And then you ended up connecting this to that. So if I want you to count the total number of carbons within your connection, okay, we are counting the straight line and not the substituents. Okay, we are counting the straight lines only and not the substituents. So if I want to count the number of carbons within the system, okay, if it was like this, I would have just counted 1, 2, 3, 4, or 1, 2, 3. Fine. But because there is a connection between this and this now, how am I going to count? It's going to be 1, 2, 3, 4, and 5. These ones are not part because they are not part of the straight stream. Okay, we count the straight line, the carbons that forms the straight chain. All right, good. In order to do that, let's come back to the system. Now I'm going to count 1, 2, and it is this carbon that is connected to this carbon, so it forms a straight chain, right? So it's going to be 1, 2, 3, 4, and 5. So I have 5 carbons in the system, right? So I'm just going to draw a 5 carbon system. 1, 2, 3, 4, 5. This is a 5 carbon system. Okay. Now, as I was counting, all right, let me label the carbon so that you see. This was carbon 1, this was carbon 2, this was carbon 3, this was 4, and this was 5. Is that not it? Now, my carbon 1, is there any substituent on it? No, there is no substituent, so I will leave it empty like that. If I come to carbon 2, check. Is there any substituent there? Yes, there is a substituent. We have oxygen attached to the carbon 2, right? You have oxygen attached to the carbon 2. Now, this time, this oxygen is not having a double bond. Okay, why is it not having a double bond? Because to prevent carbon from having more than 4 bonds, okay, we broke one of the pi bonds onto the oxygen, right? So it is obvious now we are having a negative charge attached to this oxygen. Is that not good? And that same carbon 2, there is 1 carbon attached to it. So with that one, you can put it here like this. This is it. Do you get it? Now, carbon 3, there is nothing. Carbon 4, we have double bond oxygen in there. And then carbon 5 too, there is nothing. Now, this becomes our intermediate product. This becomes our intermediate product. Okay. So, remember, the first thing, what did we do? In the Aldol reaction, we formed the carbanion. After forming the carbanion, we stabilized it with what? Resonance. And we got an enolate ion out of it, right? And then the third step, what do? We reacted the carbanion or the enolate ion with our unreacted ketone in the system. As I said, we use a weak base, so we don't expect all the bases. We don't expect all the ketones within the system to get deprotonated, right? So we have some of them unreacted that we can now come back and react our carbanion with, right? After doing that, you form an intermediate. Do you get it? Good. Now the next step has to do with protonation of this negative species. Okay, this intermediate, we need to protonate it. How do we protonate it? Don't forget from the beginning, when we were forming the carbanion, okay, our base, when we were forming the carbanion, our base, which was a hydroxyl group, okay, abstracted the proton from the alpha carbon. That is how come we have a carbanion, right? The base is still in the system, and then it is bearing our proton, okay? It's just like you sending someone to hold something for you, then you come back for it later. Okay, good. So now our base was holding the proton for us, and now it is time for us to take it back. Okay, so what happens? This is the proton. Let me write it well for you to see. So this was the proton that the base abstracted, and then this is the special. All right. Now our negatively charged oxygen comes to pick our proton, and as I said, don't forget we are picking a proton, not a hydrogen atom, right? So it has to leave without an electron. So the electron between this system and this hydrogen has to be broken onto the base. And I'm sure by this time you see it clearly, right? By now it is clear for you. Good. So now our negatively charged oxygen species abstracts our proton. The proton or the hydrogen breaks the bond onto the base. All right. So now we end up having our final Aldol product. Okay, we end up having our final Aldol product. You can pause the video and try yourself to see if you're able to write the final Aldol product. It is very simple. We have our intermediate system here, and then the intermediate product abstracted the proton from our water. Okay, the water we got when we reacted or when the base abstracted the proton. All right, don't forget the base is a hydroxyl group, and then when you add proton to it, it becomes what? Water, right? So when water donated the proton back to our negatively charged intermediate product, what will be the final product? Okay, you can try it. Pause the video and try and see if you're able to get the final Aldol product. All right. All right. So now this is the final Aldol product that we are supposed to get. Okay. And if you did it very well and you had the same thing as I wrote on the board, then congratulations. But if you had it wrong, then please pause the video, replay it, and then watch it very carefully. Make sure you understand it this time and then do it yourself. All right. Good. Good. Now there is another final step that we have to go. There is another final step that we have to go. If you are being asked, okay, whether in an exam or quiz or interview or wherever, to show the mechanism, okay, of an Aldol reaction, this will be your final product. This is where you end. This is where you end the mechanism. All right. But then, if you are being asked to proceed and give the condensation product, okay, then it means that you have to add another thing to it. There is another step that you have to add to it. And as I said, condensation has to do with the removal of water from a system. Okay. Now, to get a condensation product, we need to be able to remove water from this system. Okay, we need to be able to remove water from this system. All right. Now, how do we do it? We do this by the application of what? Heat. When we apply heat to this system, we end up removing what? Water from the system. All right. And then the removal of water here, you have to be very careful with how you do it. Okay. Now let's focus. Water is made up of what? A hydroxyl group and a proton. Two of them added together. That is what gave us water. Is that not it? Now, for us to be able to remove water from this particular product that we have gotten, what do? We have a hydroxyl group here, which is the one that is here. So we have gotten one component of the water. Now we need to be able to abstract a proton so that we can get a complete water molecule, right? Now the proton abstraction, it occurs on the alpha carbon, okay, or it occurs on the carbon in between the carbonyl system and the alcoholic system. And in between the carbonyl functional group and the alcohol functional group, what is the carbon in between them? This is the carbon in between them. And this carbon has hydrogens attached to them, right? So when you abstract any of these hydrogens, in addition to the hydroxyl group, then you what? Form water, right? And this water, because it's a good living group, it will leave the system. Okay, and once it leaves the system, what do you have? You end up having a multiple bond within the system, or a double bond for that matter. Okay, you form an alkene, and usually we call it an enone. All right, good. Let's see how it's going to look like. Let's see how it's going to look like. We have abstracted our OH in addition to one of the hydrogens in between the two functional groups here. And when that happens, we end up having a product like this. Don't forget, it was here that we took the hydroxyl group, and it was here that we took the hydrogen, right? So if I take them off, we end up having what? A double bond within the system. We end up having a double bond within the system. Please, are you following? Good. This is what we call the Aldol condensation product. It is, sorry. See, I forgot to add the keto functional group. This is how it's supposed to be. So this is what is called our Aldol condensation product. Okay, this is our Aldol condensation product. Why? Because there was a removal of water from the initial reactant. There was a removal of water from the Aldol product, and we ended up introducing what a multiple bond into the system, in addition to what our ketone group or our carbonyl group in the system. So this is what we refer to as our Aldol condensation product. Okay, and then sometimes they call it an enone. Enone because there is an in here which represents a double bond like alkenes, and then there is a ketone here which represents what a carbonyl system, right? And we usually call them none. So enone, combination of an alkene and a ketone becomes an enone, right? Yeah, so that's how come this name. So this is the Aldol condensation product, and this is an Aldol product. So keep in mind there are two things depending on what the question is asking you. If it asks you to give the Aldol condensation product, then you know you have to proceed to the final step that we just did. But if it asks you to just give the Aldol product, then you have to end it at the Aldol product, the one that we just wrote first initially. Please, are you okay? Now, there is one thing that I have to touch on before I bring this presentation to an end. If, as I said, it is compulsory, okay, it is very compulsory or important for you to remember that when you are abstracting or when you are taking water from the system, after you have taken your hydroxyl group off, if you want to abstract a proton, okay, for that matter, the proton on the carbon that is in between the two functional groups, which is this particular proton, you need to be able to what? Be mindful of the presence of the proton. There are some systems that you don't have a proton in between the two functional groups. Let's say instead of you having two hydrogen atoms here, okay, you end up having other atoms like carbon in here. And when that happens, you will not be able to what? Abstract a proton here because there is no hydrogen here to take. Is that not it? So if you have a system that is like this, okay, let's say you are given a particular ketone or an aldehyde, and then when you took it through the mechanism, you ended up having a product like this. This product does not have an alpha hydrogen here. It doesn't have any hydrogen in here, so you cannot proceed to form or produce an Aldol condensation product. If you add heat to this, okay, if you add heat to this, you will not be able to abstract water. Why? Because the hydrogen here that you need to abstract and add to this hydroxyl group to make it water is not available. Okay, so the product of this particular reaction will be what? No reaction. No reaction because there is no hydrogen to abstract. Even though there are hydrogens at the other positions, but then this is where we are interested in. This is the exact position that we need to get the hydrogen. And so far as there is no hydrogen there, don't bother yourself to what? Abstract the hydrogen. Once you do that, it means that you are forcing the system and then you end up collapsing the whole thing. Okay. Yeah. So this brings us to the end of today's, will I call it lecture or presentation? Yeah. And then I'm so grateful that you were able to stay from the beginning until now. And I pray that you get something positive out of this. Okay. If you are confused, don't worry. It means that maybe you did not watch the video on carbanions. You can go back and watch the video on carbanions, and when you come back to this particular session, trust me, you will get it. It's very simple. Don't forget to subscribe if you are new, okay? It will help us grow. You know, when you subscribe to the channel and then you share the videos, it gives me that kind of motivation to do more of it, okay? So please don't forget to subscribe, don't forget to share, don't forget to like, and most importantly, don't forget to comment. If you have any question, you can put it in the comment section. I will address it duly. All right. How will I even say? Let's say, yeah, I'll see you in the next video. All right. Bye bye.